Welcome to ALD Stories, a series chronicling the personal journeys of the people behind atomic layer deposition, untold stories of the technology, and deep dives into the history, development, and future of ALD. I'm your host, Tyler Myers, bringing you this podcast from Beneq, the home of ALD. ALD Stories is excited to welcome Professor Hele Savin from Aalto University for episode 28. Hele is a full professor in the Department of Electronics and Nanoengineering, where her work has focused on the engineering of microelectronics and photovoltaics. She is a power user of ALD, having successfully implemented the technique for surface passivation in black silicon solar cells and induced junction photodiodes. In 2017, Hele was awarded the Women's Innovation Prize from the Finnish Parliament after fabricating a black silicon solar cell with a record-breaking 22.1% efficiency. She has continued to push boundaries by creating photodiodes with over 100% external quantum efficiency, which led to IP now licensed by Finnish detector company Elfus. In this episode, Hele and I discuss how she was first exposed to ALD by Beneq, a mindset that using ALD was dirty, and how mind-blowing early ALD passivation results were. We also talk about why ALD oxides are better than thermal SiO2, the theoretical implications of breaking 100% EQE, and upcoming work in upconversion in her lab. Thanks again to Hele for her time and perspectives as an ALD end user, so grab your tea or coffee and please enjoy Aalto University's Hele Savin. Welcome to another episode of ALD Stories. I'm here with Hele Savin from Aalto University. Thank you very much for joining us today, for taking the maybe not so long trip down the road to Beneq. We're really happy to have you on the show.
Thanks for inviting me. It's my pleasure to be here.
So as we've discussed on our initial kind of call and even this morning, that this is very interesting for ALD Stories because you wouldn't necessarily consider yourself an ALD person. Your research doesn't necessarily work on fundamentals of ALD or anything like this, but you use ALD as a tool for your research. So I think this is a really great place and a great episode for people to listen to realize that ALD maybe isn't all about the fundamentals, but it is super applied, and there are people that are involved with it outside of fundamentals. So what I'd kind of like to start on then is, what is your background, your interest? I know we talked about micro and nanotechnology. How did you get into the field before you started thinking about ALD?
Yeah, okay, interesting questions. So I was thinking to go to the Helsinki University of Technology to study physics, but I still selected to study electrical engineering.
Okay.
And maybe it had something to do with Nokia at that time in Finland, which was booming, and I had my very first cell phone, and it was kind of amazing how it works, and I wanted to learn about that more. And then I remember taking the course on semiconductor technology, the basics of semiconductors, and immediately I realized there that, whoa, this is super interesting. I was lucky. I also got some funding to go to do some studies also abroad in US. I went to UC Berkeley, California, for a year, and I joined the group in microelectronics there, doing silicon technology, and I was also involved in projects with big semiconductor companies like Intel and TI, IBM, and it was super interesting to work with them and see also their labs, and also kind of my interest was really high at that time. And also I would say in Berkeley was also affecting, even though I was doing microelectronics research there, so silicon technology, in the group there were also some researchers starting to do research on photovoltaics. So I did not personally get involved, but I was kind of following them, and at the same time noticing that was early 2000, so 2001, 2002 or something like that. And then I noticed that this is going to be a big thing in the future. And then I came back to Finland, so I wanted to continue both of these fields, and especially the photovoltaics in early 2000 in Finland. Maybe the response here was not very good, because people were thinking, well, it's not a good idea. That at that time they didn't think that PV would be interesting topic in someday in Finland. So
is that because of the climate here?
Yes, because of the climate, and at that time yet there was like not so much about the like a climate and energy issues were not so big problem at that time or publicly, and PV was considered only to be kind of something to be used in South.
I see. Okay.
Yeah, so that's why it's been now really, really happy to see how things and attitudes have changed in Finland. So and I'm really happy that I kept my, like, I did not believe the others, but was stubborn and knew that this is going to be big someday. I will show you. But both for the photovoltaics and semiconductors, so we did not use ALD at that time. Even in Berkeley, the group, maybe some high-K dielectric films were deposited by the companies, but not really in the universities. And and the thing the thin film that we really were using both in the PV and microelectronics was thermally grown silicon oxide.
So you came back to Finland. Were you always expecting you were going to come back to Finland to work on these things? Was there any motivation to stay in the US at the time? I know that semiconductors happening early 2000s in the US was pretty enormous industry to be a part of.
Actually, I considered staying there. I got even job offers there, but there were some issues because I was there with the government funding, with Tekes funding, so there were some issues with visa, so you have to come back to Finland for certain years. And the reason, I forgot to tell what was the motive, like how did I came there, was that actually I was working with Finnish semiconductor industry in Finland first, was Okmetic and Murata, and there was this mass microanalog system, really a chip manufacturer also in Finland. And they kind of wanted that someone would go to the US to bring some knowledge, also state-of-the-art knowledge to back to Finland.
So spy work.
But of course in a university and doing academic research. But yeah, exactly, this is what was the purpose, and I think it succeeded very well because I learned so much there and got also the networks, and then kind of had a reason to come back also, which makes now when I'm kind of older, then I was a little bit younger and a little bit upset, like why do I have to come back? But now I realize that of course if it was paid by Finland, I have to also bring the knowledge here. And
great. So now you're back in Finland. So you're working both photovoltaics and some semiconductor processing work. But you mentioned you were only using thermal silicon oxide at that point. So for how long were you working on this before you started to get exposed to ALD, and then how were you originally exposed to ALD?
Yeah, so this thermal oxide definitely was the thing that was kind of the core expertise also in our group. So we had fully dedicated furnaces for growing the high quality thermal oxide at high temperature, and you have to keep everything super clean, and handling and everything is kind of somehow special skill, and we managed to do that well. At Aalto we got this Beneq tool around 2005 or something like that. That was actually that was I think Beneq sold the first ALD to Aalto, to our facilities. So exactly, yeah, I think it's the number one tool produced by Beneq.
Yeah, 2005 sounds about right.
Yeah. And then I think there were lots of groups. I was not involved in this because I didn't know anything about the ALDs or the purchase, so it just appeared there, and lots of groups were using it, and I think many other groups in Micronova are more like, let's say, doing MEMS or some to me like dirty research, or doing exactly this, studying weird materials and not silicon compatible at all. So I wanted to stay as far as possible from the ALD tool and be sure that no one will use our oxidation furnaces and thin films there and do not mix them. So we did not even pay attention to them at all for a very long time. And then it was around 2007, 2008, I got a phone call from Jarmo Skarp from Beneq, and who called me or came to my office with 2 scientific papers that were published in 2006 and they were showing really good results on surface passivation on crystalline silicon done by ALD aluminum oxide.
Okay.
The papers from IMEC and also Eindhoven, TU Eindhoven. And Jarmo said that, Hele, have you read about these papers? So they have some really good surface passivation results by ALD. And then I was like, I was like, did not pay attention too much. And then he kept like pushing me and, hey, let's try this and let's try this. And I still was not really willing to try. But eventually I think he came with an ALD aluminum coated wafers. And then we kind of said that, okay, we can measure the surface passivation for you, because I was like, Beneq did not have a facility to measure this surface passivation. I did not like put high priority on those samples, and then because I was really thinking that, oh, they cannot work, and okay, but let's do the measurement. And then I remember when we did the measurements and got the results, and like, because there were so many samples, it was not only one sample, but they all worked, and they were even better than our thermally grown silicon oxide, and I could not believe that. So that was really like an eye-opening, like, ALD, what's that? Something I have missed, and I have to really like, what is this? And then it is supposed to be the dirty tool in the clean room, and I had also this. I was not the only one in our group with the same attitude, or even in the field. I would say that I remember also, like, my students, I had to say, like, had the same idea, that they said, no way, we are not touching that tool. And I was showing the results. Hey, let's try if we can also do it with an Aalto tool, the same films. And then yes, I remember we did the experiments, and also they worked. Like, we did not do any process development. We had some basic ALD aluminum oxide recipe, and the results were like amazing.
That's incredible.
Yes, but it was because we had this strong attitude towards it, that it cannot work, and it cannot replace the thermal oxide. And even VTT, I remember one who are working in the same building, this group doing also semiconductors, and very very good experts, and especially at that time the group was head by Simo Eränen, who unfortunately has already passed away, but he was really my kind of like someone I asked also a lot of help, and I knew he was super good on making semiconductor and silicon devices. And I remember this discussion with Simo also, that when we got this ALD aluminum oxide result, that because he also knew that Aalto has the ALD, but had the same attitude, and I showed him the results, but he could not believe, and he was even more like,
more skeptical after
yes,
that. Yeah.
And he never even like, because we had some joint projects together, and we said that, and we were fabricating devices together, and I was proposing, hey, let's try to some of them, but he never said that.
He really didn't want to touch
not
it.
in my devices. You are not putting ALD coating on my devices, and I'm really like, I tried several times, but I could not convince him.
It's interesting.
So
I think even now in some semiconductor device markets, still some that are maybe trailing edge node technologies, and then device markets or just fields that aren't necessarily semiconductors, I find the same type of like hesitance in wanting to adopt ALD, or like it seems like too good to be true. This can't actually be how it works. We're not going to like give it the light of day. So that seems to have been pervasive over the last 20 years even.
Yeah, even though in semiconductor industry, of course, people know the ALD is used in the factories, and it has this background of high K dielectrics, but people think that these tools are still quite, and they are of course different than what we have at the universities, but still the university tools, like, it's amazing how it can actually, because maybe the background is that we are when we do semiconductor devices, we really do them in a very clean environment, so every step is super critical. And then you have some tool where you are allowed to process different materials, so usually it's like no, and something like it's not. And then one thing is that we don't have, like you said in the beginning, I don't have an ALD background, or the ALD chemistry is not very familiar to me or to my colleagues. So it's kind of like you don't know something, so then you are like don't want to use it and don't want to trust it.
Were you kind of going at it alone, just trying things out, or were there people at Aalto that were helping you learn? Were there some others that you were kind of leaning on for the knowledge transfer?
Yeah, so we were because maybe it's actually maybe we are now lucky because we have so many groups that are using ALD. So for their own purposes. So exactly. So we were mostly using the recipes that were in the tool. So it was really like just how to use the tool was of course something that someone trained to us, and then we used basically the recipes that were already there, and of course some small tuning we made every now and then, but not really like trying to make a completely grow new material or try to do new processes. That's not our thing. So we are really taking advantage of the ready-made recipes in the university by the other groups. So so that was kind of because we that was not our main research to like develop the ALD films.
Good. So then maybe we can start jumping into some of the interesting work that you've done. So I think maybe we can first touch on, and you had mentioned that earlier, the photovoltaic work that had been done. And maybe if people have heard your name before or read, they probably know that you have broken a record. I don't know if this record has now been broken a few years later, but for the highest efficiency in a black silicon photovoltaic cell. So that cell itself uses ALD for passivation, correct, on the cell. So could you explain a little bit how, well, first you got to using the black silicon, what it is, because that I think is interesting, and then whether when you started you were already thinking about using ALD, or if that came as like an afterthought.
Yeah. All right. So this black silicon is something that also was not originally developed in our group, but by other group in Micronova, and I think they did not have any optical application in mind, but more like hydrophobic surfaces and medical microfluidics and some applications like that. But when I saw also the wafer, which was like by eye looking really black, it was really looking impressive, and then also knew a little bit that this black silicon has been tried before also in maybe it was more 5-10 years ago in solar cells already, but it was somehow abandoned because no one was able to passivate this, so make the electrical because so black silicon means that it's like a nanostructures made on silicon, so really nanoscale, a little bit like nanowires. Type of surface. Not often. They can be also wires or pyramids or some rough surface in a nanometer scale, so that the structures are smaller than the wavelength of the light, and that's the reason why it absorbs so well light. And different angles and also different wavelengths, so that all what is important in solar cells, because we have different angles where the sunlight is coming, and also we have quite wide spectrum. Yeah, so but this was not then I think it was kind of abundant research topic for photovoltaics, because there was no way to passivate it. So even though you are getting good absorption, you don't get higher efficiency because you don't passivate, and you lose your electrons to the surface.
So this is because of recombination.
Recombination, yes. So we want to the photons come in and are absorbed in silicon, and then they generate electrons and holes, and those charge carriers we want to have to the contacts. And if we have a surface that is not passivated, then they are lost there, exactly because of this recombination. So, but nanostructures, passivation, ALD, like a natural, like then it was like to me like, okay, so surface passivation by ALD, why not? And then no one had tried that, like in literature. That was like really amazing, like how is that possible? But it was exactly this, that probably they did not know about ALD, this field, because they were using CVD coatings for passivation, silicon nitride, photovoltaics. That was the or just then if you wanted to make very high efficiency, use thermal oxide. So no ALD at all in photovoltaics. So then that was, I think, people just did not know the technology. So then to me it was like, okay, let's try. Of course, I did not have high hopes because I still maybe was a little bit doubtful for ALD even at that stage. But then that was really amazing, because when we coated them with the ALD aluminum oxide, and it was as good as the planar surface. So we consider millisecond like a minority carrier lifetime as kind of a value that is considered already super good. With thermal oxide, you barely reach millisecond lifetime, but with an ALD you get several milliseconds even. And now with even this black silicon, it was more than millisecond for the first trial. So it was like, come on, it works. So I think that was the, like, I would say the moment that I know that this is going to be a big thing. I did not need to do the device to know that. I mean, then later on, I knew that if we apply this to a solar cell, it will be high efficiency solar cell. So I think that was exactly the moment I remember for the rest of my life, because this was the thing. And then I also remember that we went to a conference to present the results then to the silicon photovoltaic community. So this main conference at that time, so crystalline silicon photovoltaics conference, that was 2012. So maybe 6 months after we had got these results, so not yet. We had of course submitted a paper on these results, but this was kind of the first time that we were able to kind of reveal the results to the audience. And I remember this feedback there was super good, because they were like, first, okay, thinking motivation black silicon, okay, no, not again.
Sure, we thought we got rid of this, we threw it in the trash already.
That's old stuff. And then it's like, what, milliseconds in black silicon? Like then, like everybody knew that, okay, this is a big thing.
It's fantastic. So what was the efficiency then that you reached once you made a device?
Yeah, so then later on, then we applied this. We wanted to take the most kind of the most challenging solar cell structure possible from the surface passivation point of view. So we did not take the mainstream technology, but we selected this so-called IBC cell, interdigitated back contacted cell. And that cell means that you have actually because in normal solar cells you have the charge collecting p-n junction on the front side. So the photons, and most of the photons are absorbed on the front side of or near the front side of the silicon. So they don't have much time they don't have to travel or yes. So then it's more easier to fabricate. But in IBC cells you have actually the charge collecting junctions at the backside. So when you absorb your light or your light, most of the electrons are formed on the front side. So it's super important to passivate this front surface well, and that's why this is not maybe the mainstream technology, because the passivation is not so easy, and it's more expensive to make. But we wanted to make this like a proof of concept that if we are able to demonstrate it here, then like any other cell architecture should be fine too. So for that, and I think the previous someone had tried black silicon and before, and it was with thermal oxide passivation, and it was published in Nature some years, maybe five years before us. And there, I think the efficiency was around 18, and it was considered already good good at that time because it was published in Nature. But then we got more than 22%. So and even in our cells we show that it's not limited by the black silicon or the surface passivation or the ALD field, but something that, because we of course try to do as good IBC cells as possible, but we are not collaborating with the most, like maybe in some really good universities you have like much more knowledge for making absolutely best IBC cells, so the junction and the metal contacts are those which do not have anything to do with the surface passivation. So that's kind of limiting our efficiency. So the 22 is not really, like if you apply the black silicon and ALD to, let's say now, to the state-of-the-art solar cells, then probably it would go higher. So
that's great.
And how we know this is, maybe I can introduce a parameter called external quantum efficiency, because that's also used a lot. So sometimes people talk about this efficiency and what does it mean, but this external quantum efficiency is an important parameter because it describes how many electrons one photon can generate, and typically it's considered an ideal case if one photon produces one electron. So typically one photon produces less than one electron, so you need like 10, let's say 10 photons, and then you get few electrons out. So in our solar cells we were able to show that this we had really close to 100% or even 100% external quantum efficiency. So we were able to collect each photon was able to produce this one electron, and independent of the wavelength. So that's why we knew that this was kind of, those are not limiting the efficiency, but it's more like some resistive losses or something else which are also there.
It's fantastic. So then, if those resistive things weren't there, maybe if there were some superconductors, which is now a very hot topic, that maybe the efficiency could ideally be close to whatever the EQE is then. So one thing another hot topic, I guess, for ALD community is the fact that now ALD is used in high volume manufacturing for solar cells, specifically PERC solar cells. And I think maybe I've mentioned on this podcast before, Leap Micro, the company in China from Weimin Lee, who University of Helsinki alum, to do 10,000 wafers per hour of PERC solar cells. Is it possible for black silicon cells to make it to some high volume manufacturing, or is anybody attempting to do this?
So we actually worked with one German company, SolarWorld, who was interested in actually applying this to their production line, and we managed to do already some runs with them in high volume manufacturing.
Okay, fantastic.
As a researcher was happy that I was able to see in there like mass production lines, because we had also lots of maybe more engineering issues at that time, like how fragile are these, and they are these exactly like huge mass production tools with robot handling, and then making the panels where you press the glass with high pressure, and will these nanostructures survive there, and things like that. But then we solved all those, and kind of we have some panels now made in mass production.
I'm sure going to see that production line is a very, it's a big step from just an old Beneq tool doing ALD to a huge cell production line.
Yeah. By the way, I want to say that like even though they did not, like all the other steps were then done there, but of course the company did not have ALD. So that was actually done here in this building. So the ALD coating was done here at Beneq this but also with your mass production tool, because then it was not like so many wafers. So of course we cannot do them individually with our research tool. So it was done here, kind of with the mass production tool, even though not in the same factory.
Interesting. Okay, so they were shipping everything from Germany back to here and back and forth. Okay, maybe not the most efficient way to do it,
but that was really like the proof of concept thing.
Cool, great. So then my next question is whether ALD then spurred you to think about, or I may phrase this a different way, using ALD in the black silicon cells for the surface passivation. Did it then spur some new ideas of where you wanted to use ALD, and then did that kind of drive your lab in a new direction?
Yeah, so I was not intentionally looking for that, but then I remember I saw one presentation, maybe in a conference or something, and was more in a detectors and photodiodes, and they were like it sounded like really complicated setup, that they had some 2 different mirrors where they guide the light to the silicon chip finally, and to minimize these reflection losses. So with the help of mirrors, and then somehow that was like first thing, like why do you use so complicated mirrors? Why don't you just use black silicon, because you can do it immediately on the silicon surface and without building up all this other complicated stuff around that. And then the second point was that they were again using thermal oxide there as a layer to actually form so-called the PN junction, so-called induced junction. So they use thermal oxide, which has only a minor charge, but it's enough to generate somehow like a junction into the silicon as well. So you don't, typically the PN junction is done with external doping, and you do ion implantation or diffusion or something to form the PN junction. But they had this nice idea of using this induced junction with the thermal oxide. But I also, and it worked quite nicely. But then I knew that in thermal oxide you have really small charge, small positive charge. So the junction cannot be as good as if you would use ALD and aluminum oxide, which has actually high negative charge. We actually forgot to talk earlier why the ALD aluminum oxide is better than a thermal oxide.
Yes, we did. Yes.
Yes. So the key is that in thermal oxide you have both have good interfaces, and maybe thermal oxide has a slightly better interface than ALD films, but thermal oxide has only high like a small positive charge, while ALD films can have either positive or negative charges, which are much higher, and these charges in the film will push away the carriers from the surface, so that they can't recombine there as efficiently. So in silicon oxide the carriers can come to the surface, but they don't recombine so easily because the quality is so good. But in ALD you get an extra boost because they don't even come in the first place to the surface. So
aluminum oxide ALD has a very negative charge.
Negative charge, yes. So then that presentation gave me the idea that, hey, why not to use ALD aluminum oxide as this so-called induced junction, and then also combine it with black silicon. So or not even combine it just as for planar surfaces. Both should work. And then this was something like an idea that came to my mind, and I came back to the lab and said to my researchers that let's try to do this. We haven't. This was the very first time that we fabricated photodiodes. We were not doing photodiode earlier, but somehow the idea of using black silicon and then ALD aluminum oxide as an induced junction, and then we measured the photodiode performance, and it was again like first trial, and it was really excellent. So also in photodiodes we got this external quantum efficiency close to 100%. So
okay, great. So then you did ALD on these again, and so you found external quantum efficiency about near 100, or did I read in your paper that it could even exceed 100 in this instance?
Yes, we can talk about that as well, because as I said, this was our first photodiode, so we were thinking, okay, yes, that's really good result, but since we did not have like a fabricated them before, or I did not have much background in photodiodes. What is the typical performance in such photodiodes? And then I remember, so I was just thinking, okay, let's just publish this in a normal paper and like let's see what the audience thinks. But I happened to talk also some photodiode and photodetector persons in Finland, and I showed the results to them, and then they were really saying that if this is true, you should aim really high publications.
Wow,
so
okay.
This is like, I have never seen anything like this before. So then we really realized that okay, maybe this is again a big thing, and then we also ended up having a really good publication at the end.
Well, what is the typical then efficiency for a photodiode if this was like, you know, blowing them away?
Yeah, so then it depends also on the typically they are optimized for certain wavelength. So and I would say that the UV light is especially difficult for to detect well. So that's way below 100%. So like 80-70 or something like that. So this is exactly what was interesting, and then I think also afterwards. So when we published this, of course, lots of people contacted us, and also one interesting trial that we also made was with the big CMOS camera manufacturer. So the photodiode is just a single kind of chip, so it measures the light intensity in chip, but no pictures at all. But of course, you know, in cell phone cameras, or that's a really big market where you have actually want to take an image. So that's kind of a row of photodiodes.
Right.
So it's just the matrix, and then you take and then the signal processing is done with the CMOS circuits. And of course that we cannot really make CMOS cameras in a university, because we would need a CMOS factory for that to make it a state of the art. But this company approached us and said that hey, they would like to try if this technology could be used to improve their CMOS camera efficiency. But they were also maybe still a little bit skeptical, and by the way, they, for instance, did not trust on ALD at all.
This is a common theme.
Yes. So as a surface passivation layer, so and this induced junction was totally like what they use in plantation and stuff. So, but what we did is that we took their best product. They sent these like chips to us, and then we just remove, because how they are working is that the light comes. They are often called a backside illuminated CMOS cameras. So the light comes here, and all the CMOS circuitry is here, kind of saved. So we just made the front surface black, and then deposited ALD aluminum oxide to get a good surface passivation for that. And how do they do at the moment? Like, what was the counterpart is of course no ALD, but they use no black silicon either. So they use multiple, like so many layers, thin film depositions to get this reflectance to zero.
Right.
That result also turned out to be like amazing both to them and to us, and we get this quantum efficiency much higher now in their CMOS cameras than what is it like in their production line and what we fabricated now in here in Micronova. And this paper only came out maybe 1 week or 2 weeks ago, so it's a really that's why I'm happy to advertise it now here. So this was one of the.
I'll timestamp this. That this is August 9th. Yeah. This is going to be published in a couple months. So a couple months and 2 weeks.
All right.
It was published, but I'll timestamp it so people know what it.
So I think it was
coming.
Published in August or this year.
That's fantastic. Something that was mentioned was that the quantum efficiency perhaps can be higher than 100%. So one photon can generate more than one electron. So is this something that is people expect it might be able to happen? Does this have any implications on like limits that people or theoretical things that those have proposed in the past?
Yeah, so there is so-called Shockley-Weiser limit that has been kind of defined already in 1961 when I checked this year, and that defines that's defined for solar cells and used as a basic to calculate so-called maximum theoretical energy conversion efficiency in solar cells, and that assumption is exactly based on this fact that it assumes that only one photon can generate maximum one electron. So that's considered like theoretical maximum. So how people can sometimes there is a confusion about this external quantum efficiency. The term is maybe not used correctly always. So one option is that how you can do this, that one photon actually generates more than one electron, is that you are kind of adding extra energy, you are biasing, putting a high voltage to the device so that you give extra energy to the electrons, and so they have a lot of energy to kind of give the energy further to another electron and kick out other electrons. But I think that's like and sometimes that's called like a gain, external gain. So but of course that's not used in solar cells because that would consume energy. So it doesn't make sense. But sometimes in photodetectors that's used. But then the problem is exactly the dark current or dark noise, because then you multiply also the dark current as well. So, but in our devices and solar cells, and this Shockley-Weiser limit is exactly defined when you don't have an external bias or external field. So it's really like there is no energy coming more than from the photon. And silicon has a certain band gap, so it's kind of considered that of course you cannot generate energy more than what is coming into the cells. So that's kind of the assumption behind that. And now in silicon, especially in UV range, the photons have really high energy in UV. So they have higher energy than the band gap of silicon. So that's the background, like when you are kind of able to go above the theoretical maximum, but no one has been able to do it because this UV light I mentioned earlier, it's very difficult to collect because of the surface passivation. So you always have the quantum efficiency in reality maybe 70 or 80% at maximum. Even the best solar cell efficiencies that are published nowadays they always show in the external quantum efficiency that in UV it will go down from 100%. So the maximum is around 600 nanometers, and then in UV, both because you have the reflective losses often if you are still using the silicon nitride, and then maybe not good enough passivation, and you may have some junction recombination, and so this UV light is very difficult. So at that time I was not even thinking about the theory, and of course the first idea was that okay, it must be a mistake in the measurement, so it cannot be like above the theoretical efficiency limit. So then what we did was like in one publications, I think we kind of like did we even cut the data that we don't show that it goes above, because we cannot trust it.
Pandora's box.
So someone is then speculating, but then we wanted to study it further and wanted to kind of because we also wanted to publish something in a high impact journal, so you have to have certified measurements. So we sent both our solar cells and also our photodiodes to Germany to a calibration lab, so where they do these certified measurements. And I remember their feedback also, that they said that, hey, this is the first time we measure EQE higher than 100%, but we trust our measurements, so it must be a true thing, because I was also asking like, can you trust?
Did you make a mistake also?
Yes, but they are, because this is their like profession to do has as small error in the measurements as possible. So they definitely confirmed that this is true. And then then we started to study further what could be this physics, and then we realized that the photon energies have actually so high energy that if we don't have any losses, so we have perfect surface passivation, we have induced junction, no like external dopants, we have no reflection losses, like all the losses are gone. So then you are able to see it,
That's
this
incredible.
phenomenon. So that's at least how we explain it now.
So I presume and hope that maybe this has been patented, or there's some like IP around this this technology now. Yeah.
I had a group of researchers who had also some background in this detector industry, and then they were thinking that this detector industry is not caring about too much about the money, like the cost of the cost of the device, but the performance is what they are willing to pay, and then also the volumes can be much smaller. So we could start here kind of fabrication in the in micronano. And so there was a startup company that was then established in 2017.
So this company is then locally based, making these photodiodes with the induced junction,
Yeah.
ALD induced junction.
Yes, so they are, yes, but I think they are growing, and then I don't know too much about. They're probably also planning to do fabrication elsewhere to grow further. But yes, they do some production in micronano.
That's exciting.
Yes.
How does that feel for you to see something that you worked on, like you've kind of now go off into the commercial space, even if you are not, commercially minded yourself too much?
Yeah, I think that's exactly my main motivation, and that gives me like okay, it's nice to do research and publish, and but when you see something is really being utilized and in production, so that is really rewarding. And likewise for instance for these CMOS cameras, I really look forward that someday they are like, I don't see why not ALD aluminum oxide passivation, and in some of them also black silicon on. So that is like super great. And I still see why not. I mean, it's just a question of attitude change.
Well, it's interesting. I think we're at a point right now with ALD where it's kind of on the precipice of perhaps getting into many like everyday devices. Of course, it's in all of our chips and everything from semiconductor industry that most people are familiar with. But yeah, all of these kinds of applications outside, like the image sensors and photodiodes, photovoltaics, whatever it is. I know now ALD is being used on the lenses of mobile phone cameras.
Yeah.
So all these places that maybe 20 years ago, when ALD was being first introduced to the semiconductor industry, no one ever thought it might come into these like very kind of fringe other applications that weren't being thought about. So I expect that we'll see many more inflection points for ALD in the commercial space at some point.
Yes.
So then where do you go from here? Are you working with some people in ALD at the Aalto? Are you continuing with ALD for more projects? What's the future look like?
Yeah, so first if I take an example of collaboration inside Aalto, so I work with Professor Maarit Karppinen's group, who's really the ALD person and ALD group, which we are not. So, but exactly I would say a good example of how we utilize the ALD in our research nowadays. So Maarit has developed ALD processes and films which have so-called upconversion, photon upconversion phenomenon taking place, and that means like if you are shining the film with a certain wavelength, it will be absorbed there and emitted with another wavelength. And that's especially interesting to me regarding the infrared radiation. So if we have infrared radiation, even from solar cell, let's say, some of them have so small energy and so high wavelength that they will actually, the silicon is transparent, so it will just go through it. So we are kind of losing it. So that's one big loss mechanism in silicon solar cells. So you are not able to absorb these far infrared photons at all. So I'm thinking if we put this Maritz film underneath our solar cells, and we could actually, and then even part of because they are lost already anyway,
Right.
if they have
right.
went through. So if even small part of them could be emitted to a wavelength that can be then absorbed again in silicon with any photons or electrons, then that will increase the efficiency. And nowadays we know that even small increments are interesting to the industry and relevant. So this is kind of like an example. So I have no clue how this upconversion ALD aluminum oxide recipe is made, but if it works, I'm really happy to implement it into our solar cells.
Okay, so it's infrared, basically goes through active material, reaches this upconversion layer, absorbed, and then emits as a photon that then is reabsorbed in the active layer.
For instance, yes.
Okay, that's super interesting. I have no idea how that would work perhaps either.
Yeah.
Great. So just maybe one last question. Is your group growing? Are you always looking for new students at Aalto? Are these projects that are open for new thesis students to come work on?
Yeah, so this is the life at university, that the group is changing a lot. I have had always hard time with that, to lose people when their contract ends and then they have to move on and so on. So we have had really a lot of fluctuation. I think at the highest number was close to 30% in my group, and
wow.
that was too much.
That's quite a lot.
Yes, so then I did not enjoy. Now we are around. We have been quite for a long time, for 15, which is still also. I would say that 10 would be maybe something like what I prefer, but I mean, if I meet good students, good researchers, funding has been quite successful, I must say, and so those maybe, and it looks bright also as well. But I don't have intention to grow. I somehow like this a little bit smaller group would be maybe easier to handle. Of course, then we have more postdocs who take care of the practical guidance of the students and so on. But always I'm definitely happy to get applications. So if you're interested to apply for a researcher position, either graduate student or a postdoc or research fellow, even more experienced ones, so welcome to send me a message.
Great.
I will have a look.
Fantastic. Hopefully there are some students listening who are interested, and I know we were discussing earlier that we're always trying to find people interested in semiconductor work, especially in Europe these days. So,
exactly. So yes, study semiconductors. Please select that topic. Yes.
Well, fantastic. I think that we covered so many interesting things today, and I can't thank you enough for again coming down the road from Aalto to chat with me about the work that you've done using ALD for your semiconductor and photovoltaic device work. This was really fun and super interesting. So yeah, thank you again.
Thank you so much. It was fun.
Thanks for listening to ALD Stories with Beneq. To stay updated on new episodes each month, please follow us on Spotify, Apple Podcasts, or Google Podcasts. We hope you enjoyed the show. I hope to see you again in the next one.